is the main proposition in the topic of money. So let us go through it one more time. So it says this: if you invest C0 amount of dollars with interest rate alpha, and then you will have Cn dollars after n years. The Cn is calculated in this way. So it's 1 plus alpha to the power of n times your initial capital. Okay, so we understand this, right? Okay, so now let's maybe the title "Warming Up" is not entirely correct, but let's look at a simple example just to recap further. Okay, so here's a question. Suppose the annual interest rate is 12%. Okay, it's quite high, but let's assume it's 12%. And you borrow $1,000 for 6 months, right? So how much should you repay? Right? Is the question clear? So you know the interest rate alpha is 12% for a year, but you only borrow for half a year. Okay. So now the question is, how much should you pay? Okay. Okay. So let's look at the solution. So suppose the interest rate for 6 months is X, right? Now, by the proposition, we know that after a year, you should have this amount, right? So it's 1,000 times 1 plus x to the power 2, because obviously 1 year have 6 months, right? So you have this. But on the other hand, you know the annual interest rate is 12%. So you should get this number. So therefore, you have this equation. Is this all right? And then from this equation, it's quite easy to solve x, right? So the 1,000 get canceled, then you do this. So the x is square root of 1.12 minus 1, because you have to move this one to the other side. Okay, so it's roughly 5.83%. Okay, so you should pay this amount after 6 months, right? Okay. Notice this is not equal to 6%. X is not equal to 6%. You see, if we are not very careful, we will divide this guy 12% by 2. You get 6%. But that's not the correct computation. So the correct computation will give us 5.83%. Okay? Is this all right? So, good. Okay, so now we are looking at another example. Now this time the example doesn't involve the proposition. So we are going to use this example to, how to say? So the mathematical facts behind this example is different. So let's see what it does, what it tells us. Okay, so the scenario is this. So suppose you have C dollars, and then you want to invest. So you ask, I don't know, my favorite bank, DBS. So you ask DBS to invest in some shares. Okay, let's say just invest in DBS shares. So you want to invest C dollars over a period of n months, right? So after n months, you get, you didn't get money, but you get a certain amount of shares as your return. Okay, so it's a scenario clear? So you have C dollars, you give it to the bank, and after n months, the bank return to you certain amount, X amount shares. Okay? Now, the price of the shares fluctuate. So DBS will give you two options because the price goes up and down. There are several ways of calculating it. So what is going on? Okay, so DBS give you two options. So the first option is you calculate the average price of a single share over the n months, right? And then you divide C by this P bar. You get this amount of shares. We are going to look at it we are going to have the mathematical formula in the next slides, right? So this is first option. You calculate the amount based on the average price. Okay, so this is option one. Now the option two is you, instead of using the average price, somehow you divide your money into n portions. Now each month you use this amount, C divided by n, to buy shares based on the price of the month. And then you take the sum in the end. Okay, so you have two options. Now the question is which one? Which option is good for you? Right? Which one give us more shares? Okay, so now wait. Is a question okay? Especially for those who just came in? You understand, you are with me, right? Okay, so now let's look at the solution. So first, let's make everything more precise. Okay, so let's fix some notations. So let P sub k denote the price of one share at month k, right? In the first month is P sub 1, second month P2, and so on and so forth. Okay. And use this overline P bar denote the average price of one share over the n months. In other words, the P bar is the average, right? So you add up all these, the price on each month and divide it by n. So this is the average price, okay? So now under the above scenario, in option 1, you get x1, which is C divided by this average price. You get this amount of shares. Right? This is clear. Okay. Now, in option 2, you get, okay, in the first month, you get C over n times 1 over p, right? So in the first month, you invest this amount, and then divide it by the price. In the first month, you get this amount. Okay. In the second month, you get, again, you invest C over n many dollars, and then the price for each share is P2. So you use this divided by P2. You get this amount in the second month, and so on and so forth. At the nth month, you get C divided by n times this number. Okay? So using our shorthand, this is C over n multiply the sum 1 over pi, where I goes from 1 to n, right? So this is a shorthand for 1 over p1 plus 1 over p2 plus ... plus 1 over pn. So this is the number of shares you get under option 2. Okay? So now the question becomes it becomes a mathematical problem. Which one is bigger? Which one is greater? x1 or x2? Let me repeat. So we turn this problem into a mathematical problem. So the mathematical problem is, suppose you have P1 up to Pn. Now you want to compare these two numbers. So the number x1, x2. So x1 is this. x2 is this. Okay, so you want to compare these two. Now let's work out which one is bigger. Okay, so comparing x1 and x2 actually is comparing these two numbers. Here I just copy down what we had in the previous slide. So x1 is C divided by the average price, so it's divided by this number. X2 is just the exact copy. Okay, so comparing x1 and x2 is comparing these two numbers. Okay, so it looks quite complicated. Now let's change the two terms a little bit. So C doesn't play any role because it's proportional to C, so you can cancel the C, right? So now let's flip this this fraction. So left-hand side actually is n divided by P1 plus dot 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 plus Pn. Okay, the right-hand side I just cancel C, so it's this number. So comparing the second line is the same as comparing the third line. Okay, now and then here you need to think of it. So we are going to put equal or less than or equal or bigger than equal between the two terms, right? But these numbers are all positive numbers, so I can multiply things around, right? So let's imagine, suppose this is less than or equal to, and then the same relation will hold here, because suppose here is less than or equal to, I can multiply both sides by n. It still maintain the inequality. So the left-hand side become n squared. I can move this guy to the other side, so it still keep the same inequality, right? So I'm saying comparing the third line actually is the same as comparing n squared with this funny product. Okay, so I hope this is okay. Right? So this is our problem. We are going to show that it turns out n squared actually is always less than or equal to the product. So this needs some work, right? It's not so clear. Okay. I hope you are with me up to here. So we turn this question into this mathematical question. So we want to compare these two numbers. I want to convince you that n squared is less than or equal to this product. Okay, so this is it requires some mathematics. Okay. Okay, so I need to remind you some basic facts about quadratic equations. Well, you may not link this quadratic equation with the problem we are facing, but somehow by some magic they are related. So this is the fun part. Okay, so let me remind you this basic fact about quadratic equation. Quadratic means degree 2. Is this kind of equation. Okay, recall that a quadratic polynomial is one of the form f of x equal some number times x squared plus ax squared plus bx plus c, where a, b, c are real numbers. Okay. Now you can find roots. Let's restrict ourselves among real numbers. Let's forget about complex numbers. So let's look at real numbers. So you can find the roots by this formula. You learn it from JC or from whatever, high school. Okay, so the root is equal to, I will not read it, so it's equal to this. Okay? Now the fact was, sometimes you get two roots, sometimes you get one root, sometimes you get no roots. Okay, so if the number under this square root, if b squared minus 4ac is bigger than 0, then this gives you a number, positive number. So with this plus and minus, you get two roots, right? Now, if this b squared minus 4ac equals 0, and then this term disappears. So you only get one root, right? The plus minus 0 is the same, right? So you only get one root, which is minus b over 2a. Okay? Now, if this number, b squared minus 4ac, is less than 0, and then this is not a real number. Since we only look at real roots, so this this guy has no roots in real numbers. Okay, so this is the basic fact about quadratic equations. Okay. Now we can look at it on the graph, right? For example, in the case of a bigger than 0, this parabola will facing up. Is like this. Okay, so this is the first case. Is there's no root. This is an example of the quadratic equation has no root in real numbers, because the green line is the curve of the quadratic polynomial. It doesn't cross this x-axis, so therefore it has no real root. Okay. No root in real numbers. Okay. Now, in the second case, this parabola like this the green one goes like this. So it has one root. It hits the x-axis only once, right? This corresponding to this b squared minus 4ac equals 0. Okay. Now, when this b squared minus 4ac is greater than 0, you have two roots. So the parabola goes like this. It hits x-axis at 2 points, right? So this is an example of what happening. So the message I want to send is this. So the first two cases happen precisely when f of x is bigger than or equal to 0 for any x, right? No matter which x you are looking at, the green curve is bigger than 0. In this case, the green curve is bigger than 0, but at this point it hits 0. So it's always bigger than or equal to 0. In the last case, we don't want, because for some x, it is below the value of the polynomial is less than 0. Okay, so the message I want to send is the first two cases happens. What are the first two cases? Which is f of x is always bigger than or equal to 0. In this case, only happens when this, we call it discriminant. This b squared minus 4ac is less than or equal to 0. Okay? Okay. So here's the magic. So now, what is the link between the question in the investment, right, and these quadratic equations? So here's the connection. Why do I say it's magic? Because you have to consider this one. And usually when mathematicians say consider something, it's not trivial. This is not the first thing you consider. But somehow, anyway, some clever people consider this, so we follow them. Okay, so let's look at this expression. Right? So the expression is a sum of n terms. Right? So the n terms you consider is this in this funny form. Why it is in this form will become clear in 1 minute. Okay, so the term is x times square root of pi plus 1 over square root pi, and the whole thing squared. So it is a sum of some squares, right? So f of x is a sum of n terms. Each term is in the form of a perfect square, a square. Okay. Now, here's a fact: for any real number, y, if you square it, is always bigger than or equal to 0. Okay. For example, okay, if y is a positive number, certainly y squared is bigger than or equal to 0. If y is 0, certainly y squared is 0. If y is negative, let's say y is minus 1, but when you multiply minus 1 with itself, the minus sign get cancelled, right? So you still get 1. It's still positive. So no matter which real number you pick, the square is always bigger than or equal to 0. Okay? Now apply to f of x. F of x is sum of some squares. So therefore, it's a sum of non-negative numbers. And then if you have several non-negative numbers, when you add them, it's still non-negative, right? There's no chance you get negative. So the key observation is this f of x is always bigger than or equal to 0. Okay? Now, on the other hand, this f of x is a quadratic polynomial. You see, let's calculate what is f of x. So it is a sum of some squares. So let's open up this square. So there's simple calculation. You'll say you square the first term, which give you pi times x squared. And then you have, so the formula says, the formula of a plus b squared says a squared plus 2ab plus b squared, right? So 2ab means 2 times this number multiply the other number. So it's this. Now the b squared, the last one square is 1 over pi because the square root, when you square it, become pi. Okay? So it is a sum of these guys, right? So I'm just opening up this bracket. Now if you add these together, you get this sum. If you are not familiar with these shorthand, you can write it in a, you can expand it into a long term. So this is, for example, this is p1 squared plus something, then p2 squared plus something, then p3 all the way, right? So when you add them up, you get p1 plus p2 plus p3, everything multiply x squared, right? So that, again, in shorthand, you get this guy times x squared. Okay, so f of x actually is in this form. So f of x is the sum of pi times x squared plus 2nx. So why here I get 2n? Where does this n comes from? When I equal 1, I get 2x. When I equal 2, I also get 2x, right? So this is the sum of n terms. For each term, I'll get 2x. I have n terms, I'll get 2nx. Right? Again, you can do it by expanding it, but it's an easy observation. Now the same reason goes, the last term you get sum of 1 over pi. Okay, so you get this quadratic polynomial. Okay, so in short, this quadratic polynomial is always non-negative, no matter what x you put in. Okay, so now we are going to use the fact. Okay, so by the fact earlier, we must have this b squared minus 4ac less than or equal to 0, where a is the coefficient of x squared, b is the guy in the middle, c is the last term, right? Okay. So here is capital A, here is capital B, here is capital C. Right? By the facts, we must have this thing less than or equal to 0. Now what is this? What is b squared minus 4ac? Well, can you? Okay, so b squared is 4 times n squared. Okay, minus 4ac is minus 4 times this sum times the other sum. So it's 4 times this. Now if you move things around, so this is 4n squared, this is minus 4 times the product. So if you move this to the other side, cancel the 4, you get n squared is less than or equal to this funny product. Okay? So the conclusion is option 2 is better than option 1 because this number is bigger than or equal to n squared. Okay, so this is the solution. So the solution use some mathematical facts, and in the end we get the result. Any questions? Is this okay? Okay, so So let's continue. Last time I feel that lots of you actually have very good mathematical background. Some of you are from math department, some of you from physics and engineering, or so you are very good at math. So I can sort of tell you more tricks, and so let's try. Okay, so here we can have another way of showing this result. Just now we showed that n squared is less than or equal to the product, right? So now I want to give you another argument. This argument probably is more interesting. Okay, so let's try. So this argument uses some fact about arithmetic mean and geometric mean. I don't know whether you heard of it when you are in JC. If not, let's go through it. It's interesting. Okay, so I want to show this inequality. So I say that it's suffices. This is a mathematical way. So I only need to show the following. Okay, I only need to show that this number n divided by this sum is less than or equal to the average of these PIs. If I'm able to show this, I can cross multiply. I'll get n squared less than or equal to the product. Okay? Now to show this, I introduce something in the middle. The something in the middle is the nth root of the product. Okay, so people give names of these things. So this is called harmonic mean of the PIs. The thing in the middle is called geometric mean. This is the average is called arithmetic mean. Okay, so what is going on? Right? Okay, so when we have two numbers, the geometric mean actually has a geometric interpretation. Okay, so let's see. So I want to convince you. Okay, sorry. The setting was you give me P and Q. I want to return you the so-called geometric mean, which is H, right? Okay. When n equal 2, geometric mean is the square root of the product, right? So this H will be the square root of P times Q. Okay? So now what is H? The H is obtained this way. So I draw a line segment of length P. And then continue, I have a line segment of length Q. Now then I draw another line which is perpendicular with this PQ. Right? So this is the where I locate H. And then I draw a circle, a half circle, with radius half of P plus Q. So imagine that here is a middle point, and then I draw a circle. The circle will hit the red line somewhere. Right? So this point will give me the H. Try again. Draw P and Q, and then use a center as the center, and radius half of the average of P plus Q, right? And then you draw this half circle. The half circle will hit this line, the red line somewhere, and then this is the H. Okay. Now the half circle, I don't know whether you learned this geometric fact or not. Sorry. If you have the half circle, this angle is 90 degrees. Okay, so this is a fact. Okay, so we have this situation. We have a right-angled triangle here, and also we have two smaller right-angled triangle. This is one. This is the other one. Okay. Now, why H squared is PQ? This is by the Pythagoras theorem. So you see, if you look at the big triangle, you have R squared plus S squared equal to P plus Q squared, right? So this is, the theorem says R squared plus S squared equal P plus Q squared, because this is a right-angled triangle. Okay, so in other words, r squared plus s squared equal this number, p squared plus 2pq plus q squared. Okay. Now, if you look at this right angle triangle, you would have r squared actually equal to p squared plus h squared, right? R squared equal p squared plus h squared, because this is a right angle triangle. By the same reason, s squared is equal to h squared plus q squared. So you have this. So these two lines are equal. Well, it's very easy to see. You can cancel p squared, you can cancel q squared, and then here you have 2h squared. Here you have 2pq. So therefore, h squared is pq. So this is the geometric explanation of the geometric mean. Okay, so now I'm going to show the fact. So first, let's see this claim. The geometric mean is always less than or equal to the arithmetic mean. From the picture, it's clear. Why? Because from picture, the arithmetic mean is average of p plus q, is somewhere here. Now this is imagine this is a circle. So this, from the center to this point, is a radius, right? So the radius is bigger than h because this is a right angle triangle. So this line is bigger than this, right? So from the picture, it's quite clear. Let's do some calculation. It's also very clear. So I want to show. Okay, so I want to show this. So this is n equal 2 case of geometric mean less than arithmetic mean. So you consider this square. So square root p minus square root q square. As we said before, this is always non-negative, right? And then you expand this square, you get this. So this number is always non-negative. Then you can move this guy to the left, divided by 2. So you get this. So this is the n equal 2 case of geometric mean less than arithmetic mean. Now, we want to show the harmonic mean is less than or equal to geometric mean. But this is quite easy. This follows from this geometric mean less than arithmetic mean, because you use the number 1 over p, 1 over p1, and 1 over p2 instead of p1, p2. So you get this is the geometric mean of the two fractions. Now the right-hand side is arithmetic mean of the two fractions. So you have geometric mean less than or equal to arithmetic mean, right? But however, if you flip them, you also flip the inequality, right? 1 over the, okay. Left-hand side is less than or equal to right-hand side. When you do 1 over them, certainly the left-hand side become bigger, right? So therefore, if you flip them, you get the geometric mean of this, but the right-hand side become harmonic mean, right? So you get harmonic mean less than or equal to geometric mean, right? So this argument holds for n. So although I write it for 2, this, suppose you have lots of terms here, you can do the same argument. So from this, we only need to show the geometric mean is less than arithmetic mean. Now, how do we show this? So for n equal 2 is easy. How do we get in general? Because the nth root is difficult. So here's a trick. So first you get all the power of 2. For example, let's look at the case when n equal 4, which is double the number 2. Okay, so you do this. So apply the case n equal 2 to these two numbers. The first number is this, root of p1 times p2. The second number is the root of p3 times p4, right? Now, this is a geometric mean of p1 and p2, so it's less than or equal to the arithmetic mean. The same thing holds for the second term, right? So therefore, this funny guy is less than or equal to this one, right? Now, the guy in the middle, again, looks like a geometric mean of two numbers. One is P1 plus P2 divided by 2. The other one is this. So again, you can use geometric mean less than or equal to arithmetic mean. So you get this. Right? So you have the double square root of these guys is less than or equal to this. Now you can simplify. So because you take square root twice, you take the fourth root. Here you divide 2 twice, so you divide 4, divided by 4, right? So therefore you get the formula for the case n equals 4. Now you can do the same argument. You can do from 4, you can go to 8, you can go to 16, and so on and so forth. So you get lots of instance of geometric mean less than or equal to arithmetic mean for the power of 2. Okay. But there are lots of things which are not power of 2. How do you get them? So here's the trick. So let's use n equals 3 as an example. So now I want to use 4 to get 3. So here's the trick. So how do I get the case n equals 3? Let's look at n equals 4 case, right? So it's fourth root of product of 4 things is less than or equal to the average of 4 numbers. So in the formula for n equals 4, I replace the last number, P4, by the average, by the arithmetic mean of the first 3 numbers. Okay. Let P4 be P1 plus P2 plus P3 divided by 3. Plug in to the formula for n equals 4. So you get the fourth root of this product is less than or equal to the average of the sum of the 4 numbers, right? Because we already have n equals 4, I can do this. And then we are going to massage the terms and so that we get what we want. Okay, so first, you know the first root is the same as raising it to the quarter, to the power of 1/4. So these things give you this power, and the sum, again, you get the average raised to the power 1/4. Now here, I claim the right-hand side is this. Can you see? Because P1 plus P2 plus P3 is 3 times this number. So on top you have, so imagine you have 3 over 3 here. So you have 4 over 3 on top. And that 4 and this 4 get cancelled. So you get just the average. You can do it on paper. It's quite easy. It's not hard. Okay. So the right-hand side, you can simplify it to here. Okay? And then you can cancel the power. So you see here you have the power of 1. Here you have power of a quarter. So you divide it by the power of quarter, you get the right-hand side, you get 3/4. Right? So you have this number is less than or equal to the average raised to the power 3/4. And then you can do, okay, raise it to the power 4, you get here, the left-hand side is just the product. The right-hand side become the power of 3, right? So then you take the cubic root, you'll get this. Right? So by some simple manipulation of power, you'll get the cubic root of the product is less than or equal to this average. So this is the argument from 4 to 3. Now this is not a mathematical class, so I'll just say you can do the same argument to get k minus 1 case from n equal k case. So imagine, so here I go from 4 to 3. The same argument goes from 8 to 7 and 7 to 6, and you can do the same trick. It's a good exercise for you to try it. Is this okay? Probably you have learned it in JC, right? How many of you have seen this before? Okay, there are someone. Maybe lots of them in watching the webcast will know this, but I think this is fun. This is it's not too obvious, so it's okay. Anyway, so let's continue. So now we are moving to the second topic of today. I'm going to establish the mathematical facts I mentioned in the first lecture. Okay, so somehow these mathematical facts is related to the next topic. So they are materials coming from the textbook. So the reference is Yokyang's textbook, sections 2.1 and 2.2, but somehow I swapped the order. Okay, so let's continue. Okay, so the section 2.2 says talk about arithmetic progressions. I guess you are more familiar with this than the arithmetic means. Okay, so let's look at the definition. So an arithmetic progression is a sequence of numbers of this form. So you start from a number a, and then the second term is a plus d for some fixed number d. And then you keep adding the amount, the d amount, right? So the second term is a plus d. Then you add d one more time. So this is a plus 2d. And then the next term will be a plus 3d. So each time you add one more portion of d. Okay. Okay, so number a is called the first term, of course, it's the first term. And each number is obtained from the preceding ones by adding a fixed number d. The d is called common difference. So you just keep adding the same number d, you get the whole sequence. So the typical example is for example, this is a example of arithmetic progression. So this example comes from the calculation of simple interest, right? So suppose you deposit $100, and then the interest rate is 5%, and if I interpret the interest rate in a simple way, every year you get $5. So the first year you get 100 plus 5. The second year is 100 plus 10, and then you plus 15, plus 20, and so on and so forth, right? So this is an example of arithmetic progression. Okay. Now, very often we are interested in taking the sum of the arithmetic progression, right? In other words, we are going to add these things together. So the sum is called arithmetic series. Okay, so you just add the first n plus 1 terms together. Okay. So let's look at some concrete example. So there's some number called triangular numbers. Triangular because it corresponding to the triangles like this. Okay, so the triangular numbers Tn is the arithmetic series with this particular first term and the common difference. So T1 is just 1. T2 is, okay, so it's a triangle. So the first one is 1, and then the second line is 2, right? So you add them. T2 is 3. T3, okay, so you form a triangle in this way. So this is 1, and then you have 2, you have 3. So T3 is 1 plus 2 plus 3, right? T4 is 1 plus 2 plus 3 plus 4. Well, you can read this way also, but it's still 1 plus 2 plus 3 plus 4. Okay. So in terms of formulas, okay, T1 is just 1. T2 is 1 plus 2 is 3. T3 is 1 plus 2 plus 3, which is 6. T4 is 1 plus 2 plus 3 plus 4 equal 10. Okay, so these numbers are called triangular numbers. Okay. Now, can we find the general terms? So we want to find the explicit formula for the triangular numbers. Okay, so the theorem says the triangular number Tn actually is given by this closed term. So Tn, by definition, is the sum of 1 plus 2 plus 3 plus dot 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 plus n. And then the result is, it turns out to be half of n times n plus 1. Okay. Does it make sense? Is this always a whole number? Okay. We are adding some integers together. The result must be an integer. But here you divide it by half. Is it possible that this guy is not divisible by half? No? Okay, so, well, lots of you know, right? I know you are good at math. So you see that if n is an even number, so you can divide n by 2. So this gives you a whole number. Now, in the unlucky case, n is an odd number. If n is odd, then n plus 1 will be even. So the 2 can be canceled from this n plus 1. So no matter what n, whether n is even or odd, you can always divide it, you can always divide 2 of this product. So this always, the right-hand side is always a whole number. Okay, so how do we prove this? So the proof goes like this. So we arrange the terms. So we write Tn as it is, right? So it's 1 plus 2 plus dot 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 all the way to n. Now we write Tn one more time, but we change the order. We start from n and then go down to n plus 1, n minus 1, and n minus 2, and so on and so forth. In the end, we hit 2 and 1. So we write it forward and we write it backward. Okay. So after doing this, we add these two lines together. So the left-hand side gives you 2 times Tn. The right-hand side, okay, this is n plus 1. Now the second term is 2 plus n minus 1. So it's again another copy of n plus 1, right? Now if you go term by term, you gain 1 on the first copy, but you lose 1 on the second copy. So therefore, if you add them, it's always n plus 1, right? So the 2 times Tn is n plus 1 plus n plus 1 all the way n copies. Okay? So it is equal to n times n plus 1. Well, then Tn is just divided by 2. So, right? So this is a very easy calculation. Now, actually, this is a trick by, I'm sure you heard of this story, right? So this is Gauss, one of the best mathematicians throughout history. Okay, so the story goes. Okay, so I copied down from the internet. It's quite new, but the story was very old. So the story goes like when Gauss was a kid, right? Maybe 7 years old. When he enters the elementary school, the teacher gave the class an exercise. So the teacher asked the class to add the integers from 1 to 100. So 1 plus 2 plus 3 plus 4 plus dot 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 all the way to 100. Right? So, well, for the elementary school students, it takes a while to add. But for Gauss, he used more or less what we did, right? So what Gauss did is this. You pair 1 with 100, 2 with 99, 3 with 98, right? So you get, so in some sense, it's just like what we did. So you write it forward and you write it backwards. And then in the end, you get 50 copies of 101. So immediately Gauss gets the sum, which is 5,050. Okay, so actually probably you have heard of this when you are in elementary school, but anyway, so this is a story. Now, the triangular number is an example of this arithmetic series. Now, in general, if you understand what's going on for triangular numbers, you'll understand how to find the sum of this arithmetic series, right? So the conclusion is, if you add these n plus 1 numbers, you'll get this. Sorry, why this is n plus 1? Because the first term without d. So the first term actually is a plus 0d, right? So you have to count 0, 1, 2. So how to say? Here you have n terms for sure, because this corresponding to 1, this corresponding to 2. So these you have n terms, but this a will give you another term. So it's n plus 1 terms on the left-hand side. Right? So when you add them, you get, the conclusion is you get this number. Okay? Now I guess you know what is going on. So we are going to do the same thing. We write it forward, and then we write it backwards. Right? So you get these two, and then you add them. So each term will be 2a plus nd. Now altogether you have n plus 1 terms, so 2 times the sum is this one. So therefore an is of this. Right? So this is exactly the same as the triangular numbers. Okay. Questions? Okay, good. Now let's look at some examples. So the first example is this. This is a arithmetic series, right? 1 plus 3 plus 5, so the d is 2, all the way to 2n minus 1. Now if you plug in the formula into the theorem, you get n squared. But this particular series is known have a geometric proof. So, sorry. Before I talk about these dots, you are okay with the result, right? So you can plug in the formula of you can plug in into this theorem by taking a equal 1, d equal 2, and then you can get the result. But it happens that the sum of the odd numbers, you can give a geometric proof. You see here is 1, then you add 3, you get 4, right? So you get 2 by 2 square. And then the next one is you add 5, you get a perfect square with 3 dots on each side, right? And then you add 7, then you get another square. So therefore, from the picture, you get the sum of odd numbers happens to be the square. Okay? The next one has no nice geometric picture, so you have to use the theorem. Just plug in. So this is when a equal 1, d equals 3. You add the sum, use the theorem, you get this number. Okay. Now, this probably is the last example in the arithmetic progression. So let's finish this and then have a break. Okay. So I took the example from the book, the textbook. This is example 2.2, example 4 in the section 2.2. Okay. So here is the problem. So the problem says we draw n lines on the plane, on the plane. So imagine this is a plane. We are going to draw n lines. Okay. So this will form a number of mutually non-overlapping regions in the plane. For example, if you draw one line, you cut the plane into 2 regions, right? Now, if you draw 2 lines, you cut the plane into 4 regions. Okay, here's one, all the way to the top, and there's one to the left, there's one to the bottom, there's one to the right. So you have 4 regions, and so on and so forth. I will explain this in a moment. Okay. So the question is, if you draw n lines on the plane, what is the maximum number of the regions you can form. Are you with me? So, right, this, if you draw one line, you will form two regions. If you draw two lines, you form, the maximum number is 4 regions. If you are if you are not very careful, you can have 3 regions. You can have 3 regions, because you can draw one here and draw the other one parallel to it, and then you get 3 instead of 4, right? Of course, in order to get maximum number, you want to do this. You don't want to draw the parallel line. Okay, so repeat the question. Draw n lines. What is the maximum number of regions you can form? Okay? So the solution is by looking at this table. This table says, okay, the first row is the number of lines. The second row is the number of regions. Okay? But it's probably not so obvious to find the pattern. However, if you look at the additional regions created, this is easy to follow. This is just 1, 2, 3, 4, all the way to n. So let me explain this. So the next slide is the explanation in words, but let's use this picture. Okay, so when n equals 0, you didn't draw any line, so there's one region. The whole plane is one region. Now, suppose you draw one line. You will cut the region into 2 parts. So you add one more region, right? So the additional region created is 1. Okay, so the number is 2, right? Now, if you have 2 lines, this line will cross the first line. So originally you have 2 regions. When you do this, the first region is split into half. Then the second region, okay, the region 1 was split into half. The region 2 also split into half. So you add 2 more regions, right? So here, if you draw 2 lines, you add 2 more regions. Now let's look at what's going on for 3. For 3, you have to draw a line, but this line will only cross the 2 lines once, right? So before you cross the first line, you create one region. That's here. Now, between the first given line and the second given line, you create another region, right? Then after the second line, you create another region. So altogether, you create 1, 2, 3 regions. Right? You cannot split the top because, unfortunately, the line is not a curve. You cannot turn it, right? So I hope it is clear that when n equals 3, you add 3 more regions. Let's do it one more time, right? So assuming this line, the horizontal line is the one newly added, I claim that I will create 3 more regions, right? So let's do it one more time. There are 2 given lines. Before I hit the first given line, I create one region. Between the first one and second one, I create another region. After the second one, I create another one. So I create 3 new regions. Right? And then you can see for 4, you cross 3 lines, right? Do the same. Before you hit first line in one region, between 1 and 2 another, 2 and 3 another, and after 3 is another. So so if you have 4 lines, you create 4 regions. Okay? So now the total region is you just add everything up. Right? So is this okay? Now here are the explanation in words. So we already did the explanation by looking at the picture. So I will not read the words. Okay. So in general, for n lines, you get this sum. Because originally you have 1, then you create 1 more, 2 more, 3 more, 4 more, and so on and so forth. So in the end, you get this sum. So this is just, the first one is leave it alone. The rest is just a triangular number, right? So this is 1 plus the Tn, the triangular number, but we have calculated this triangular number, so we get this, and then this is the answer. You may have another way, but I guess probably we'll take a break, and you can, if you are interested, you can try this. So let's take a break, and we'll continue to talk about geometric series in a moment. Let's see. Can you see? How do I focus this? Okay. So just now, there are several questions about the proof of this geometric mean is less or equal to arithmetic mean, right? So we are showing this by looking at the numbers. So the general case is okay. So for n, it says the nth root of the product is less or equal to the average of where do you focus? Right. So the number n when the number n change, we have, for example, we change n to n plus 1. So we have p1 up to pn plus 1. So we have n plus 1 numbers. And also the root and the denominator also change, right? So it becomes n plus 1. Okay. So now, just now, the question is, what did I do? I mean, how do I show this? So what I did is this. So here's a number line, right? So I start from n equal 2. So I check n equal 2, this is true. I can't. Okay, let me try one more time. So this is a number. This is a number line. So what I did is I first show n equal 2 is true, right? And then I jump to n equal 4. Right? Then I wave my hand, say, if you know n equal 4, then you know n equal 8, and then you move to n equal 16. Every time you double, you keep going, right? So you tick lots of numbers, but at the same time you leave lots of gaps, right? So this is the second step. So okay. So step 1, n equal 2. Step 2, from n we go to 2n, right? So from 2 we go to 4, from 4 we go to 8, from 8 we go to 16, so on and so forth. Okay, step 3. Actually, we go from n to n minus 1. You see, I only give you example, so I only showed how to go from n equal 4 to n equal 3. But, okay, so what I did is this. From n equal 4 to n equal 3. Right, so this guy get ticked. Now the claim is the same argument shows from n equal 8, you can go to n equal 7. And then from 7, you can go to 6. And the same thing here. So by going backwards, you can fill out the gaps. This is a plan. Now, how do I go backwards? How do I? This is. Okay. So how do I go? Okay, so to go from n to n minus 1, you have to use this trick. You have to look at the nth root of p1 dot 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 pn minus 1. The last one you have to replace you replace the last pn by the average of the n minus 1. And then the geometric mean less than or equal to arithmetic mean tells you this is less than equal to n over p1 plus dot 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 plus pn minus 1 plus n minus 1 plus the arithmetic mean of the n minus 1 numbers. And then you have to simplify. What we did is a concrete example, go from 4 to 3. But in general, you can go from n to n minus 1 using the same trick. Since you asked, so let me explain this. You have other ways. Just now, somebody says they probably know other ways to prove it. But this is one of the ways. Okay. All right, so if you have more questions, we can talk after the class. So let me go back to the lecture and continue to finish the topics. So here I have to press PC. Ah, good. Okay. Okay, so let's continue. So the next topic is we go from arithmetic progression to geometric progression. Okay, so the definition is we are going to have a sequence in this form. So it's A start from the first term A. The second term is obtained by multiply A by a fixed number R. Just now we add to A by a fixed number D, right? Now instead of adding, we multiply, right? So the second term is A times R, and then A times R one more time. So it's A times R squared. Then the next term is you multiply the same R to the previous term. So you get A times R to the power 3, right? So it says, so this is an example of geometric progression. So each number is obtained from the preceding ones by multiplying by the same number R. So the R is called the common ratio, right? So this is a geometric progression. Now, as before, we are interested in the sum of this geometric progression. So it's called geometric series. So for example, we want to add A plus AR squared plus all the way to A times R to the power of n, right? So in shorthand, this is the sum of from I equals 0. That is the term A, right? And then plus AR, then this is I equal 1, then AR squared is I equal 2, all the way to I equal n, right? So this is the geometric series, okay? Okay, so we have used this formula. So this is, I label it mathematical fact 2. So in the previous lecture, we used this formula. We say that if you add this geometric series, you get a fraction. You get this term. Okay. So now we are going to show it. We are going to prove it. It's not hard. Okay. So this is a more general. Geometric series, right? So the theorem says the value of a geometric series for r is not equal 1 because we are going to divide r minus 1. So when r equal 1, it's wrong. Right? So for r is not 1 is given by this formula. So this is, you add a, you take the sum a plus ar plus dot 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 plus a times r to the n, you get this term. You see here in the concrete example, the a is 1, the r is x, and then this n is k minus 1. So you get a is 1, right? So you don't need to look at a. The n is k minus 1. So this is this is x to the k minus x minus 1 divided by 1 minus x, right? So we get this. So now what is the proof? Well, it's almost as simple as the previous one. So let Sn denote the sum we want to find. So this is the sum. Now you multiply r on both sides. So left-hand side you get r times Sn. The right-hand side, a times r become ar, and ar times r become ar squared, and so on and so forth. So the last term, ar to the power n, becomes a times r to the power n plus 1, right? And then you subtracting. You can imagine you multiply the first equation by minus 1, then add to the second one. So when you do this, so imagine we add a minus sign on the first equation, then add to the second equation. What do we have? So left-hand side is rsn minus sn, because you minus this term, minus sn. Now here, lots of terms are cancelled, right? Because you have a minus sign here, minus a survive, minus a is here survive. The minus ar with positive ar get cancelled, right? So these two terms get cancelled. Now minus ar square and positive ar square get cancelled, right? So this one disappear, and then this term also disappear, because this is minus a times r to the n, but here you have a positive a times r to the n. So these two also cancel. So the only surviving term is here. So it's a times r to the n plus 1, right? So if you multiply minus 1 to the first equation, then add to the second equation, you get this. And then it's very easy to solve, right? So that you get Sn equal, you just divide. Okay? So here's a question for you. What happens if r equal 1? You cannot use this formula, but can you find the sum? Yes, right? Because as you know, that okay, when r equal 1, you get a all the way. So certainly you know how to find it, right? Anyway, so okay, so what are the examples? So the examples to use geometric series is again, the textbook give this example, Tower of Hanoi. So it's a game for kids, right? So you have 3 poles, and then you have several, they call it slabs or discs here, from smaller ones to the bigger ones. Now the game is you have to move the all these slabs from A to, let's say, to B. The rule is you can never put a bigger one on top of a small one. You have to keep the order. right? So okay, so let me read this. So there are 3 vertical poles, A, B, and C. So 5 circular slabs of different radii, so from small to big, and each within a hole in the center. So you can put the slabs on the pole, okay? So that it will rest on the, with a hole in the center, rest on top of each other as shown in the figure here. So what is the minimum number of steps needed to transfer all the slabs to the pole B? If at each step no slabs is allowed to rest on top of a smaller slabs in the same pole. In other words, you keep the order, okay? Now, well, the solution goes like this. Suppose you only have 2 slabs. That is extremely easy, right? So you need 3 steps because you move the top, the smallest to C. Okay, so A, B, C. Then you move it here, and then move the larger one to B, then move back. So 3 steps, okay? Now, let's find the recursive formula. So let AN be the minimum number of steps required to move a tower of n slabs. This example says A2 is 3. Okay, we are interested in finding AN. Now the key observation the key observation is the following. So suppose there are n slabs. So let us label them 1, 2, etc. from top to the bottom. Okay. So the key observation is this. So ask ourselves, when can we move the n slab, the largest one, to pole B? Now, this happens exactly when the first n-1 slabs form a tower in pole C, right? So here, when can we move the last one to B? We can only do this by moving the top 4 levels, 4 slabs to C, right here, and then we can move the last one to B. This is the key observation. So if you understand this, the rest is easier. Right? So the minimum number of the steps to achieve this is AN minus 1. So you have to move the top n minus 1 levels to another pole. So that takes AN minus 1 steps. So it takes AN minus 1 steps to move the first n minus 1 slab to C. 1 more step to move the n slab from A to B. And then it takes another AN minus 1 steps to move back, to move the n minus 1 slabs from C to B. So the recurrence relation is AN equal 1 plus 2 times AN minus 1, right? So here you get AN minus 1 step. Here you get 1 step. Then you have another AN minus 1 step. So this is the relation, okay? Okay, so then in our case, n equal 5. So this is extremely slow. Okay, so by the formula, A5 is 1 plus 2 times A4. Now what is A4? A4 is 1 plus 2 times A3, right? So it is equal to 1 plus 2 squared times A3. Now what is A3? A3 is 1 plus 2 times A2. Well, you don't need to so it's very easy to calculate. So in the end, you find A5 is the sum of the geometric series, right? By the formula, you get 31. Okay? So now, can you figure out what is AN in general? So it's just 1 plus 2 squared plus all the way to n minus 1, right? So this is, it will be 2 to the n minus 1 in general. Okay, okay, so now last time we talked about the growth. So there is a fact we use. We say that exponential growth is much faster than linear growth. Now I'm trying to establish the fact. You can use your calculator to, you can use your computer to draw curves, but let's look at the table. So indeed the table, I copied the table from some lecture in computer science. So in computer science, they care about so-called complexity. So we only need to observe the last 3 columns because these things are about log. It is important to computer science. So we just want to know the exponential against polynomial. Okay, so we concentrate on the last 3 columns. The big O means order. It's more or less like this. Okay, so when n equal 1, okay, everybody is about the same. Sorry, can you see this is n squared? This is n to the power 3. This is 2 to the n. So the last column is exponential. These 2 columns are polynomial. Okay, so let's look at when I increase n, how fast these numbers go. Okay, so the n takes 1, 2, 4, 8, 16, 32, 64. So n squared is not much. So the last one is only 4,000 something. Okay, now the n cubed is much bigger, but is still less than 1 million. Okay, you do this. Now 2 to the power of n. At the very beginning, it's not so fast, right? So here's 2 and 4 and 16. Now when n equal 8, you get 256 is smaller than n cubed. But next level, this is already quite big. Now if you look at when n equals 32, this is a huge number, right? It's much, much bigger than the others. If you look at n equals 64, this is 1.84 times 10 to the power 19. So it's very, very, very long. Okay, I'm sure you have heard of this story, right? So the chessboard and whether you use wheat or rice. So the story, okay, you can read the story from the textbook, but roughly says there's an Indian king, right? So there's a very smart person who invented chess, and then the king was very happy. So he want to give the reward to the inventor. So the inventor says, my request was very humble. So you put 1 wheat or one grain of rice on the first on the chessboard. You put it on the first square, and then the next square you double it, right? So the 1 grain of rice, 2 grains of rice, 4 and 8, and so on and so forth. So this is my request. The king, at the very beginning, he was very happy. He says, this is nothing, right? You just, it doesn't grow too fast. But it turns out this is an impossible, reward, because the amount of the number of grains is this. So this is more or less 18 times, sorry, 1.8 times 10 to the 19. So it's such a long. This is the number of grains the king would give to the inventor. Now, how big is this is? So it weighs about. This is from Wikipedia. It's about, I don't know how to read. So this many tons. Okay. Now this is about 1,645 times the global production of wheat in this year. Now, the story is supposed to happen in 17th century India. And so probably if the king pays, he is still paying, right? So it's is a huge number. So 2 to the 64 is huge, right? So that probably give you some idea of exponential growth is really, really fast. I think in future we are going to come back to the topic again when we talk about some kind of complexity or whatever. So, but the message to take home is exponential is fast. Okay. All right. So there's last 2 or slides talking about exponential function and logarithm functions, because last time somebody says they haven't seen what log is. So let's quickly go through these. Okay. So very often we talk about the exponential function, but it turns out this is actually a family of functions. You can use the word exponential function to describe many things, but those things more or less the same. Okay. So let's see. So we start from the power is an integer. So let's define 2 to the n is you multiply 2 n times, right? So this is an example of exponential function where the argument, the variable is n, right? So this is f of n is 2 to the n. When you change n, you change the number of copies of 2. Okay, so this is an example of exponential function as a function of natural numbers. Okay. Now, this 2 you can vary. You can change 2 to 4, to 7, or to 10. So you can even you can change the 2 to a real number. For example, to I don't know, to square root 2 or something. So you can change the base. So the a to the n is also a exponential function, right? Now in calculus, I don't know. I think many of you are from physics or engineering. You learn some calculus. So in calculus, you actually allow the power to be non-integer. For example, if x is a fraction, actually it's like taking roots. You know that, right? So if x is a rational number, you can use you know how to do it. Even for x is a real number, you can here you need some knowledge in calculus. You have to use a continuous extension. So because the function is a continuous function, so you take limit. But this is not a math course, so we are not so careful. So from calculus, you learn that you can think of the exponential function as a function of real numbers. Okay? Now, you can also think of exponential function as a function of 2 variables. For example, you look at x to the power of y. So here, both x and y can change, right? Or you can think of exponential function as this funny e to the x, where e is a famous constant called Euler constant. The value of e is roughly this number. So this is often used in mathematics. Probably in real life, the 2 to the n is often used. Okay. So exponential function more or less is all of the form some number to the power of some other number. When you change the power, you get the exponential function. Okay? So now the nice property about exponential function is this. So if you multiply a to the x to a to the y, the power become a sum, right? Now if you raise it, if you first have a to the power of x, then raise it to the power of y, you get a to the power x times y, right? And also the derivative of this e to the x is very nice. It's still e to the x. Actually, there's a story, there's a joke, but I'm running out of time. I will skip the joke. Okay, so let's continue for the logarithm, and then that's about it. Okay, so exponential function a to the x, if a is bigger than 1, is strictly increasing. So you can find its inverse, right? So in other words, so the inverse is called a logarithm. For example, if 10 to the x equal y, and then x is the log base 10 applied to y. Right? So the inverse function means if you know the value, you want to find the argument. Right? So the argument is x, so x is log 10 y. Okay. The same for it, let's look at one more example. So log 2 of 32 is 5 because 2 to the 5 is 32. So now to find the inverse of 32, you get 5. Right? So log 2 base 2 of 32 is 5. Okay. Now the inverse of this e to the x, some people call it natural exponentiation, is called natural log. Is denoted by ln, ln of x, so it is base e. Now the property of the log is log of a product becomes the sum, and log of x to the power y is y times log x. Now the derivative of log is 1 over x. Okay. Now what I owe you is this. There's a fact when x is small, log of 1 plus x is more or less x. Right? We mentioned this. This is the fact 0. So let's look at numerical values. If x is 0.5, this guy is 0.4. Not so close. But when x is small, let's say 0.2 then becomes 0.18. When x is 0.1, this is almost 0.1, right? Now, if you get smaller, these get closer and closer. So it's indeed roughly the same. But this is numerical value. To get the sort of the proof, again, you need calculus. So in calculus, you learn something called Taylor expansion or whatever. So you can write log of 1 plus x into a series. So when x is small, x squared is even smaller, right? For example, when x is 0.1, x squared is 0.01, right? So it's even smaller. So the tails can be ignored. So log of 1 plus x is more or less just x. So this is a reason why this formula is true. Okay? So that's all for the day. Thanks. Okay, take 1 minute to hear the joke. Maybe some of you have heard of the joke. So there is a, let's say it's a math department. So there's a say student who was, okay, let's say there's a teacher who is quite annoying, right? So he always like to say, I'm going to differentiate you. Sorry. You know taking derivative is differentiate, right? So he always telling his colleague, be careful, I'm going to differentiate you. So it's like a threat, right? So people get annoyed, right? So who wants to be differentiated, right? So he was telling this to everybody. But one day, he was telling the head of the department. So he was doing the same trick, right? So he come to the head office, and then he talked to the head, and then he say the same thing again. Say, be careful, I'm going to differentiate you. Then the head says, go ahead, I am the exponential function. So that's, anyways. Okay, so.